So I'm going to do the teardown of this fingerprint reader, but I just checked the mail at my house and I just got to realize that this was an addendum. This is something I actually ordered. This is part of the ongoing power meter project. This came from Oh Harap. This is solder paste. And then in here is the solder paste stencil I ordered for some of the boards for the power meter project. So it's like actually a thing. Interesting. So these are just cute things to help you kind of keep your board aligned. And then somewhere in here should be my Captain solder paste stencil. Yep. So there we are. Paste mask for my my power boards and my power meter boards. This is the first product I've done where I haven't applied my solder paste by hand. I have a pneumatic syringe system I built, and I've always used that. So, pretty cool. It's also really cheap. I looked around. Pololu does solder paste stencils too, but they don't have the same precision, and they're just done on Mylar, and they cost about as much. You know, this is 25 bucks for an 11 by 17, up to 11 by 17. And it was so cheap, I don't know why people would go to Pololu when there's you know, you can get a much bigger stencil for less money. And it's done in Kapton too, which is really sturdy crap. Let me just stick that under my scope where I will then proceed to forget about it. Anyways. Beverage. Much better. Yeah, this is just, you know, obviously China special solder paste, but it was also, you know, 8 bucks for 50 grams, which should keep me for plenty of time. Anyways, so this is a BioMatch Finger 4500. I guess it gives you the finger. Lots of buttons. As I said, I think this is designed for integration into like a home alarm system or a commercial alarm system because it's got lots of, you know, it's got lots of screw terminals, and about the only people who like screw terminals are alarm companies. This is also interesting. It's got a little switch. I wonder if this is like an override mode or something. So, since I don't know what voltage this wants, I'm just going to start at 5 volts and kind of go up from there. Of course, it's also possible, but it's entirely possible it's broken. It is drawing no current. It's ground and F ground. Oh. Okay, just started drawing power. It is drawing 180 milliamps. So, there's nothing at 5. Let's try 12. Ha! So, magic pass. Enter user ID 1. It looks like it has a whole bunch of other mildly annoying crap going on. So first thing I noticed, the LCD's nicely backed, but that's nice of them. Seems like I'm probably not going to get anywhere. It's neat that it powers up. I was hoping I could get the actual fingerprint reader to, you know, at least light. But anyways, so it's just kind of neat. Alright, well, that isn't really going anywhere. It takes 12 volts anyway. So, just remove these little jumper leads. Alright. So it looks like there's only one screw. And it's a plastic threaded screw. So I think this back is intended to come off because I don't know how you'd use these mounting holes otherwise. Yep. So obviously you mount this on the wall and your cable's poking through the hole. So this is fairly interesting. We can see that we have probably 2 or 3 boards. This is obviously for the display. This is interesting. This is the fingerprint reader, and it looks like the fingerprint reader is basically a module. I wonder to what extent this is, you know, kind of self-integrated. I know SparkFun at least sells a few fingerprint readers that are basically, you know, there's a ribbon connector, cable that connects to them, and then the fingerprint reader is just a unit. So this, you know, just nice straight up, you know, FFC connectors. So here's the actual CPU board. So we've got a really big, so this is a strong arm. And then we have, you know, all the various oddments. Let me change lenses. So here we are. So the processor on here is a strong arm FADES 1100AF L2100517 Intel 1997. This is quite old. 1997. Another thing you might notice is look at the size of this sucker. I wonder if they're doing the fingerprint stuff on this processor. It wouldn't surprise me. You know, considering the date, 1997, this seems to be fairly old. I don't think they could have integrated everything they'd need with regard to, you know, the processing onto this little tiny board here. You know, it's got some passage down there that we'll look at when I take that apart, but I don't think they could have fit everything into this, you know, into that little board. So it wouldn't surprise me if the reason this is just an absolutely ginormous honking micro is because they needed all that crunch to do the fingerprint recognition. Over here we have some Hynix GM71VS65163 CLT5. That's going to be SRAM. And then that is Intel Flash. So I'd like to put the chips in all sorts of different directions. TE28F160 U1350371B. So that looks like it's going to be Flash. And then you can also see this, it's kind of in the way. So if you look at all of these parallel traces, this looks like this is probably like an addressing bus of some sort. Let's see here to this 74FCT 16425 or 164245. Is that just an octal latch? Isn't that what the 245 is? I mean, I don't know. This might be a 1642245, or it might be 74245. I'm not too sure how that works. It's a 48-pin TSSOP. I don't know what that is, ZMC or D. UL634H256. That could be another SRAM of some weird-ass types. Now look at that, there's more of these. Here are more of these 74FCT 164245. There's a bunch of them by IDT. Wouldn't surprise me if that's some sort of buffering. Here's a OVX3245. Seems like there's lots of really big parallel stuff going through here. You can see here's all these screw terminals, send plus, send minus, 45 minus, 45 plus. That's probably RS45. Ground and EXIT. Over here we have VCC ground, F ground, COM, NC, NO, WIG0 and WIG1, RxD, TXD, and ground. That sounds like serial. And then I think all of these pins are this FFC. This is a very coarse pitch FFC. You can kind of see trace, 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 trace. It looks like 0.127. Or 1.27 millimeter, I mean. Here we just have some little X9313. I wonder if that's the part number. CPEX 3232. I bet that's a serial converter. It wouldn't surprise me. Hey, LM1117. 3.3 volt regulator. That's a bog standard part. Here's a crystal, 32 kilohertz, probably an RTC, and yep, there's the RTC. That is a DS1302 Dallas semiconductor. There's just some 7407 Jelly Bean logic. I bet that's another voltage regulator, though I don't know what it is. Caps. Little resistor arrays. Here's another crystal, another 32 kilohertz crystal. That's interesting. I wonder if this has another RTC in it. Processor, or excuse me, another voltage regulator. Probably. And then we have a where are my Q-tips? Hold on one second. There they are. I fell behind my scope again. Alright. clock speed. Is that really 8 megahertz? So that is a, wow, 3.6864 megahertz. Really? That's really small, low. I wonder if they're PLLing that up somewhere. It's the only thing I can think of. Or it could be 33.6864 and the first 3 is not... No, I don't see space for another 3. That's a really low clock speed. I wonder why that's so low. And then obviously on the other side the button panel is, so I think that that's probably what these through holes are for. Anyways, let us pop this board out. So actually another thing I just noticed is there's a little tack button here. And there's actually a, oh that's interesting, look at this. There's another button here, that's going to be the tamper button. So basically, this is going to be held pressed, and probably what happens is when that's released, it dumps the NVM, the non-volatile memory or something like that, so that if somebody tries to take this off the wall, you know, to fidget with the internals or something, it'll trigger. And so this is going to be like an anti-tamper mechanism. There's another 6P205. That may be another voltage regulator or something. You know, one of the things I noticed is I would expect there to be like a big relay of some sort in this area. Oh hey look, incidentally, that's a poly fuse. And there's a diode. There may be reverse bias protection because, you know, this is basically a lot for electricians to hook up. You know, so you can't expect them to, know hot from positive, or, you know, realize that swapping the leads does in fact cause bad things to happen, because if you wire that light bulb backwards, it works fine, so why should electronics be any different? I'm just talking shit. Anyways, so, ooh, hello. So, relay, buzzer, battery back, and then this looks like an HD 44, or one of those, you know, just an off-the-shelf. Also, I see some, interesting, I see some mobs. 1 second, lens job. So here is the other side, and the first thing I notice is, wow, look at that, all the buttons have LEDs. It's very nice. So there's our little relay, which is probably responsible for the NC and the NO. The other thing you notice is Z104, Z103. Those are almost definitely metal oxide varistors, which are basically surge protection. So we have a big LM2576. That's like an off-the-shelf simple switcher from National, just a little 5 volt. And I think the fact it's not actually negative 5 volts, it's LM2576S-5.0. But I think nevertheless it's still a positive regulator. Some diodes. DS75176 from National. Let's see, I think this Q-tip still has some alcohol on it. 03AB, yeah, so that's actually not sure what that is. Maybe another, it's probably analog related. So this is interesting. This is a Cosmo part. I believe that's a little itty bitty solid state relay. You know, it's basically, it's a photo isolated solid state relay. So it's got, basically, it's like an opto triac or something along those lines, an opto FET. You know, only good for a few hundred milliamps, but that's all you need, you know, sometimes. And that's connected right up to there, which is the SEN plus and the SEN minus. Actually, no, wait, it's on, no, it's on the middle. Yeah, I'm not entirely certain where that goes. This is, you know, one thing I noticed is that this is a many-layer board, because you can see it's got an internal layer. Let's see, is there a layer key anywhere around the edges? That's interesting. Look at that. We have a cut in one of the internal layers. So it appears they have, you know, I would guess that that means that the layer immediately under the surface is the power plane, because I doubt they're going to have cuts in the ground plane. At least not around the micro. I mean, maybe in some of the power section here. But I definitely don't see any nice convenient layer indicators. There's your reset button and the memory purge or whatever it is button. Here's the connector for the fingerprint reader, and you notice that it is sucked down into internal layers. So I think this is probably a 6-layer board, predominantly because I don't see those traces. Wow, 6-layer, that's pretty huge. Anyway, so there we just have a 74HC244 Z506, Z505. Those are probably Zener. I bet these are protection diodes of some sort. Z102. Yeah, I bet. I mean, you know, because remember, this is intended to go into God knows what. Oh, that's nice. Look at that. It's the graphical LCD anode cathode for backlight VVE. So this is intended to go into a security system where, you know, people are like rubbing the wires together with sticks or something. Who the hell knows? So, you know, it has to be fairly robust. That's actually interesting. iFinger 4000L Rev E 2001-61. What is a 2001? The processor's 4 years old. I guess this might have been a fairly long-lived line. But I guess that means the processor. Huh. It means the processor was 4 years old when they built the board. But iFinger, the branding on the casing is not iFinger. It's also 4500, not 4000. That's interesting. I wonder if the difference between the 4000 and the 4500 is just, you know, basically just software, because maybe they flashed this with the new software rev. Actually, there's an interesting idea. Well, first of all, there's a whole lot of LEDs behind that, this big, interesting F key thing, which appears to be like a directional button, though it doesn't really feel like it. And also, apparently, the center bit lights up. Considering these LEDs, I bet it lights up either multiple colors. Yeah, they're multiple colors because you can see the color difference. But it's a 4-way button. Yeah, it's quite interesting. So you can see this is a nice, kind of nice. They have the pin out there. Kind of a little fluffy, grungy. CAD161. That's an interesting little board. Anyways, yeah, you can see this. Here's the that power switch, which actually, yeah, so power comes in right here and it goes to the central terminal, and it looks like when it's there it's turned on, when it's here it's turned off. We have a 16-volt cap. This is presumably gives your DC to DC for your 5-volt rail, which is then LDO down to 3.3 for the micro. Here's the beeper, and that is a 5.5 volt. 0.047 farad. So that's the battery, like the RTC back cap. You know, 0.047. That probably also battery backs like a lot of the fingerprint information. Lens switch. Because I'd be surprised if they. Because I'd be surprised if they're keeping the fingerprint data in non-volatile memory. You know, because that would mean somebody could. You know, I guess I don't know how security nuts they are on this thing, but somebody could, you know, basically rip the unit off the wall and desolder the flash or EEPROM and pull the data, or who the hell knows. So many of these, they're, you know, the firmware and the software is very well designed, and yet there's, like, if anyone has watches Mythbusters, there's, you know, it's always interesting to see how all the attacks against like fingerprint stuff, you know, because Mythbusters discovered. You know, I think they took like an image of a fingerprint and they printed it out on some paper and like licked the paper and squished it against the, you know, the surface, and voila, you're in. You know, so a lot of these, it seems like the way that these things can be circumvented is very low tech, or, you know, it's very much, you know, targeting the fingerprint reading aspect rather than targeting, you know, some, you know, involved high tech attack against the software. It just turns out that, you know, biometrics are just kind of stupid. You know, I mean, if you're trying to, you know, it's not like they're, like if you're trying to guard a high security institution, you know, and you have malevolent actors, you know, biometrics, it keeps you really secure until somebody kills someone and cuts their finger off. It's kind of a focusing on the wrong things. So this is a Huno. Or is that a C? C-H-U-N-N-O? Chuno? Sounds vaguely like a curse word. Sounds vaguely impolite. It's not exactly what you want your business name to sound like. Something somebody would call somebody else. Derogatory term. So this is the bit that really does interest me the most in this whole thing. Let's just start taking some of these screws out. I suspect that behind this panel is whatever the backlight is. Most of these use red light. I think mostly because it's... I guess it's not absorbed by blood. I don't actually know. I wonder what the science behind the coloring is. I have no idea. Have I worked for biomedical companies? Yes. Did I understand anything? Nope. Anyways, these are some really impressively tiny screws. I think this is a 00 Phillips and it barely works. And then so here we are. Here's our two little itty bitty LEDs, complete with a connector. Does not seem to be too particularly meaningful. There we are. So, okie dokie. So on the bottom of this board there's not much of interest. There's just two diodes, a bunch of resistors, and a U2, which from its 5-pin package is either like a single logic chip or probably a voltage regulator, with my money being on the latter. Yep. So that is a fine threaded screw going into plastic, because they could, I guess. A rather long screw too. So I wonder what's on the other side. Again, I don't know where most of the logic in this particular fingerprint scanner is. I've seen some that look exactly like this but do everything internally. I guess we will. Yep. So that is a rather interesting image sensor. It's an image sensor, but there's a lot of other stuff on there too. And then we have lenses. So let me change lenses once again. So here is the sensor in this device, and as you can see, it's got my pointer's a little bit bent. That's better. So you can see that this dark area is going to be the actual image sensor, and I would imagine that these horizontal sections here are going to be part of the readout mechanism. That they're kind of enormous. That may be the ADC or something like that. But I wonder what all that is. It might be like bus decoder or something. This could just be it's far more complicated than most image sensors are. I don't know actually what's going on. There may, in fact, this may be, like an image sensor, and then the rest of everything is done on here. You can see that it goes pin, actually that's interesting. The pin 1 is right in the middle. So pin 1 to 6, 7 to 18, 19 to 36, or 19 to 30, 31 to 42, 43, so that must be 44, 45, 46, 47. It's a 48 pin like ceramic LQFP. And another thing you can see is if you look at the wire bonds, they're only using these pins and these pins, which is kind of interesting. You can also see it looks like right here to this pin, pin 42 is actually a double bond, which may be grounding or something, or that may be a test point. Let's see, can I get a closer focus? 1 second. More light. More light. Brah. So yeah, you can kind of see the actually that looks, there might be a whole microprocessor on here for all I know. I mean, it depends on the size of the feature size, but you can see that there's a a fair amount of logic there, and then there's these big horizontal buses, horizontal and vertical, So that may be like an integrated fingerprint management IC. I'm not entirely certain. There we go, that's as close as this lens will focus. But you can see that there's definitely a lot of interesting stuff in there. And the other thing is, if you look at... so if you look at this kind of this structure here, it's not contiguous, which makes me think that that's some sort of like prom or something like that. I don't have a microscope that goes any closer though, unfortunately, but you can really see some of the structure. I mean, you can see that here's this double bond in the corner I was talking about. This looks to be wedge bonded, or it's ball and wedge bonded. Basically, the ends that go to the chip are ball bonds, and the other end are probably just wedge bonds. But you can see that these are the unpopular, the unbonded. Get them off where you asshole. It also looks like it's bonded with aluminium. The two metals that wire bond well are gold and aluminium, and obviously for cost-conscious stuff they use aluminium. But this is your actual sensor area. Just interesting structures. I mean, look at all of that. I wish I had a better microscope. Oh well. But yeah, it looks like 99% of this is just done in the sensor. You know, I wonder what the communication interface to the sensor looks like. It'd be interesting to know. And then, you know, this is just like a LGA type thing. And I knocked the thing off. And then on the other side we just have that one device I was talking about, which might actually be a diode, considering it only looks like 2 of the pins are connected. And those are not diodes, those are tantalums, and that actually looks somewhat hand-worked from the horrible soldering. That one looks stock. Test point. 33 ohm resistor. So that 33 ohm resistor is involved in the backlight, because the backlight connector is right in this area here. You can also see some interesting power routing. Look at the, you know, they obviously are sharing these 2 pins for one connection. Actually, that's weird. Look at that, they've got a via, and then they've got a whole bunch of narrow traces running to one of the pads. I guess that might be like ground or something, but kind of weird structures. Ceramic caps, lots of resistors. These look like termination resistors or something like that. 22 ohm resistors, 103. Okay, anyways, let's look at the optical assembly now. So here's the optical assembly, and you can see that there's a little lens in there. That may actually be metal. Not sure how this comes apart. So looking in here, the optical assembly is going to be focused on this plane. So I'm not sure how this works. There has to be some sort of bent object, you know, some bent optics, because basically the lens has to be looking flat at this surface, which is clearly at an angle. I'm actually kind of surprised a lot of these don't have a flat surface on the end rather than this cocked surface. You can also see it appears this is a solid prism. Oh yeah, actually look at that. So, oh, interesting. Okay, so, ooh, I see how this works. Oh, that's cool. Okay, it's using FTIR, frustrated total internal reflection. One second. So right now we're looking into the end of it, and you can see that because this is basically a prism, we're looking into the area where the lens looks in, and we're basically looking at this little section of matte white, black paint. But if I stick my finger on here, the areas where my finger comes into contact, it basically it frustrates the internal reflection, which is what FTIR, frustrated total internal reflection. So in this case, it's just frustrated internal reflection. And what happens is, rather than reflecting off that surface because my finger is contacting it, it changes the index of refraction, and therefore the light kind of exits through my finger, and therefore it looks a much brighter color. So what happens in here is the red LED shines in through this flat white strip, and it's basically shining on your finger. So what happens is, normally that light just doesn't go anywhere, but when it bounces off your finger, in the area where your finger is in contact, it will, you know, basically, so what you'll get is you'll get a image that looks like a mixture of black and red, you know, basically dependent on where you have your finger, you know, changing the, you know, the index of refraction of that, the optical intersection between your finger and the prism. So that's really clever. So that's how they work. You can also see that I guess that they have to, the f-stop has to be pretty small, because it's going to have to keep the entire, you know, basically this entire depth in focus. So that may constrain the optics slightly. I guess they can just assume you're going to be able to hold your finger on this flat surface for maybe a half a second. So they can probably integrate for a long time. So they don't need a particularly optically fast lens. Also, hey, now you have my fingerprints. But that's cool. So that's also why you need to press your finger pretty firmly, because if not, you know, you don't get a very good coupling. But I wonder how many of these use the FTIR technique like that, because that's going to generate a very nice high contrast image of your finger. Another thing is here you can kind of see how what's going on is that the contact of your finger is not really, it's changing the index of refraction. So basically, when light reflects off a surface, like an internal surface here, what makes it reflect, as I understand it, I don't really understand optics that well, is the fact that there's a difference in the index of refraction between the glass and the air. So when your finger comes in contact like this, it changes that, you know, kind of the disconnect between those two indexes of refraction. You have the index of refraction of your skin oil and the index of refraction of the material, which is much, you know, more similar. So another thing you can see is that as I change this angle, you can see how it basically entirely goes away, because it's right at that angle, you know, kind of, that's the critical index of refraction. This is why if you go, you dive underwater in a pool and you look up, right above you, because you're looking perpendicular to the surface of the water, you can see out. But as that angle decreases, you start to see, you know, it starts to reflect back into the pool. It's a similar thing. You can see that that threshold is right at that angle right there. It's a critical angle. So it goes from completely reflective to completely transmissive in a very narrow, you know, basically intersection degree of the very narrow, you know, basically a narrow angle. That's a cool example right there. Anyways, so in here we just have the lens assembly, which indeed does look to be that's a very small lens. It actually looks like there may be a physical aperture in there. One second. So here's the actual lens. I'm not too sure how this goes together, if it inserts in there. So first of all, you can see that from the surface, you know, from a perpendicular surface, this prism is actually held. It's not, you know, basically it's not totally flat. It's actually cocked up a little bit, which may just be some angle optimization. I don't know. Let's see if I can't push this lens assembly out. How does this go together? Kind of looks like the lens assembly snaps in almost from that little. Yep. So here is our lens assembly, and you can see there's, can't tell, is that actually glass? Yeah, that's a real glass lens too. So one thing I notice is looking in there, look at how small that looks. You know, whereas this is a fairly fast lens, but if you look in here, it's obviously like it looks like the entire diameter of the lens. You know, so you can actually kind of see the slightly corrugated, focus on the surface. So you can see the kind of the slightly corrugated steps of the aperture. You know, so down in there is the iris, which closes and opens depending on how much light it wants to let in. Whereas with this lens, if you look in there, that's frickin' tiny. I mean, from either end, here's from the back end, you can see the little tiny dot. You know, I mean, this one's similar, but I mean, this is a fairly fast lens, but that's still. I think I want to see if there's actually an aperture in there. So that's nice. This little. Okay, yeah, there is indeed an actual plastic aperture in there. So. turn? Yeah, rotate it a little bit. This appears to be more metal. Okay, yeah, now it's loose. So this is probably the actual element that focuses. They focus the lens by moving this in and out. So the first thing we can see is this is a 2-element optical system. There's just this element and the other one. So let's see, that sits in there. I don't have the proper wrenches, but I do have spudgers. So yeah, so here's our rear element lens, and there's the aperture. So that probably gives this lens, you know, kind of amusingly enough, a very small or a large f-stop. So it's probably like f10 or f12 or something in that range. I don't actually know the focal distance, but yeah. So basically, what that does is I don't think I can explain it that well. But what happens is so basically f-stop numbers are inversely correlated. Small f-stop is actually a large number, and so an f2.0 is a much larger. It lets in much more light than say an f8. You know, this lens, this is the macro lens I use. This is a very for what it is, this is a 150mm lens. It's a very fast lens. This is an f2.8 lens. You know, the lens that I'm currently on this camera right now, I believe is f3.5 to f4.5 over the focus range, which is slow. But I have plenty of light. You know, I can just turn on the light. So when I say this is like probably an f8 or f10, somewhere in there, it means it doesn't let in a lot of light. But also what happens is that the faster the lens, basically the larger the aperture, you know, the more light it lets in, the narrower what's called the depth of field is. And the depth of field is basically, you know, as you go from the lens, you know, into the distance, there's going to be a range which is in focus. And the smaller your aperture is, the larger the f-stop number is, the smaller the aperture, the more that is in focus. So by going with a very small aperture with a very large f-stop number, that means that a very large quantity of what's in the field of view will be in focus, which is how I think they, you know, accommodate the fact that they have to have the entire surface of the prism in focus, which basically means their depth of field has to be at least, you know, this deep, and it's also very close to the lens. I mean, they don't have a lot of distance. But anyways, yeah, it's an interesting little itty bitty lens assembly. Just such a tiny aperture. That's got to be like a millimeter. Anyways, that's a really interesting piece of equipment. I wish I knew more about some of these devices, but yeah, that's what's inside a fingerprint reader. They work using the frustrated internal reflection principle, apparently. Something I didn't know. And I hope you enjoyed that, and I will have the other stuff torn down over the next few days, I think.